can't find it anywhere. So can you post on this one? Also send it out to Greg. Maybe she was the last person to post. You should be here. Morning, everyone. Starting a minute late today. Some days are like that. Let's give you 30 seconds to complete your attendance poll. And unfortunately, I'm missing my microphone today, so my clip on, so I'm going to have to stand next to who's next. But I'll try to do a reasonable job of it anyway, right? Okay. Can we move on? Right.
I can't see the poll.
You can't see.
It's on.
What's up? Okay, so we've gone through deep neural networks as classifiers, as predictors. We're going to deal with a new problem. And finally, we also saw in the last class that they're capable of representing data at various levels. So the new problem we are going to address is how we can use these things to generate data. So you're given a large collection, say, of images, of faces. Can we use this collection of data to train a network to generate new portraits? So for this, the problem is basically that of characterizing the distribution of the of facial images and then drawing a sample from this distribution. But then how do you even characterize this distribution? Or for example, you might have a large collection of landscape images, and we want to use these to train the network to generate new images of landscapes. Again, we must characterize the distribution and draw a sample from this distribution. Then how do we characterize the distribution? So we saw in the last class that data can be thought of as roughly lying on some kind of a manifold. So the hypothesis is that the data are distributed in a curved or otherwise nonlinear manifold in high dimensional space. Now, this has to be true because what is the only kind of data that occupies all space uniformly? Anyone? What would that be? It's just got to be noise, right? Unstructured. The moment we begin imposing structure on data, basically we are restricting the data. And so the more data structure we impose, the more we restrict it. And so you might have million pixel images or 5 million pixel images, but that 5 million pixel image is not occupying, the collection of all possible 5 million pixel images which represent valid pictures of landscapes don't occupy the entire 5 million dimensional space. They're going to be in some subregion of it which is very structured, and just has to be. And so our hypothesis is that the data are distributed on this curved or nonlinear manifold in this high dimensional space, and the principal components of all instances of the data lie on this manifold. So if you want to generate data from this class, we have to pick a sample from this manifold. Question, how do we characterize the manifold? And what's a good strategy for selecting a data instance from the manifold? So for this, let's go back and remember the VAE, right? The autoencoder. So the autoencoder basically learned to, we remember that the decoder portion of the autoencoder captured the manifold, the curved manifold of the data, particularly if the autoencoder had nonlinear activations. And we also saw that deeper and more complex autoencoders are able to capture complex manifolds. And so we already know that the autoencoder, the decoder portion of the autoencoder, learns to characterize the manifold that data lie in, such that when you activate this the decoder using any arbitrary input, it's only able to generate data from this manifold. And we also saw that if you train the autoencoder properly, then that manifold actually learns to represent the underlying nature of the data. And so we saw examples like in the case of music, where once I trained the autoencoder on samples of music, subsequently the decoder, when excited, produced new data which sounded like notes from the instrument that it was trained on, and so on. And so, using the same principle, we could assume that if I trained an autoencoder on lots and lots of collections of images, then this autoencoder is going to learn the curved manifold of image data. And subsequently, if I just use the decoder of the autoencoder and excited it with any odd input, what it would generate would look like valid images of, say, faces, if that's what I trained the autoencoder on. So this would be a hypothesis. But then we ran into an issue, even when we were doing this. We found that although the decoder of the autoencoder does learn to characterize the manifold of the data in the regions where you have training data, when you go off of it, strange things can happen. So here, for example, when I train the data using the autoencoder using data from this spiral, then the decoder learned the structure of the spiral mostly. But then if you just fed different z values to the decoder of this AE, at some point there are some values of z, the decoder doesn't continue to just produce data on the spiral. You see this horizontal skip. At some point the decoder sort of went off the path and made a skip. Similarly, when you began feeding it new z values outside the range of what it had seen in the training data, then it no longer follows the spiral, it goes off and wanders elsewhere. So both within the space of examples, training examples, and both and outside, in regions where the z values have not been seen, the behavior of the decoder, of the autoencoder in general, can be unpredictable. So the solution to this is that if I'm going to be training the autoencoder on data from a particular class, so that when I excite the decoder, it generates more data from the same class, I want to make sure that the z values that I feed into the decoder are typical for the class. But then, what do you mean by saying the z values are typical for the class? It means that the z values that I feed in must themselves come from the natural distribution of z's for the class. But what is this distribution? Because, I mean, the whole model is kind of artificial, right? You fed it faces, facial images, it generated facial images. There's some arbitrary latent variable z in the middle. So what do we know about the distribution of valid z's in the space of z's? We don't, right? So here's your first problem. Okay, 10 seconds, guys. All right. Does someone on Zoom want to answer the first question? Is there anybody on Zoom?
It's true.
True. Okay, for the second one, guys, which of the statements are true? Anyone? The second? Right. So the decoder of the autoencoder can only generate data on the low-dimensional surface or manifold in the space. That we know. And what is the dimensionality of this manifold? You can actually make some predictions. Whatever the dimensionality of the latent variable is, it cannot be greater than that. It could be lesser, but cannot be greater than that. So the dimensionality of z is the upper bound on the dimensionality of this manifold, right? So now we want to pick z values that are typical, but we don't know what z values are typical. We do have the advantage that we define the z through our model and through our learning. So what we can do is to impose a distribution on z. When training the autoencoder, I can explicitly impose a constraint on z saying there is some distribution p of z and that z can only come from this distribution. And a typical distribution of this kind is a standard Gaussian, standard normal, zero mean unit variance Gaussian. And we like the zero mean unit variance Gaussian because it has some very nice property. The Gaussian, for a given variance, the Gaussian distribution is known to be the least informative distribution, meaning it has the highest entropy of all distributions with the same variance. So we like to work with something where we are not imposing any more requirements than essential. But then again, this is for a given variance. What variance makes sense? Since we want to make it scaling invariant, unit variance kind of makes sense. And so if we could somehow constrain the model so that the z values come from the standard Gaussian, then to generate novel inputs of the kind that the model has been trained on, all we need to do is to sample z from the standard Gaussian and then pass it through the decoder of the AE, and whatever comes out should, in principle, look like the kind of data that you train the model on. For example, if you train it on faces, what comes out should look like a face. But then how do we train this model? So again, here's what we did when we trained the autoencoder. We fed it some input, it generated some output. We tried to minimize the error between the input and the output. We still want to do the same thing, but now we have an additional constraint. We want the constraint that the distribution of z, the latent variable, should follow a pre-specified form like the standard Gaussian. So how do we do this? Here's the model again. I'm redrawing it. We have an encoder E with its parameters theta that takes in the data and generates the latent variable z. And then the decoder D with its parameters phi, which transforms the z back to the data. And the autoencoder, which is to say the parameters theta and z, are trained to minimize the error between x and x hat. But then we want to impose this additional constraint that P of z must be a standard Gaussian, right? How do we do this? Now here's, for that, let's go back and consider the properties of isotropic standard Gaussians. Isotropic meaning the same variance in every dimension. Now here again, I want to mention that the standard Gaussian is not a scalar. Its z can be in any number of dimensions, whatever we specify. All this means is that the various dimensions are independent of one another, and in each dimension the variance is 1. So z lies in some low dimensional subspace. So here's the property of isotropic Gaussians. We all know what Gaussians look like, the standard bell-shaped distribution, right? And furthermore, because this is the Gaussian is isotropic, meaning its variance is an identity matrix. That means the variance along every dimension is identity, number one. Second, that the various dimensions are independent of one another, so the joint distribution of z1 and z2 is going to be the product of the distributions of z1 and the distribution of z2, p of z1 times p of z2. And for each of these z's, the individual marginal distribution is also going to be a standard Gaussian. Now, what does a standard Gaussian distribution look like? So here's the formula. P of z is 1 over square root of 2 pi raised to d, where d is the dimensionality of z, times e raised to minus 0.5, the norm of z squared. It's basically z minus mean squared, but the mean is 0, right? So it's so the norm of z squared. And so if I look at the log probability of this, it's minus 0.5 d log 2 pi minus 0.5 norm of z squared. It's just the log of this term on top. So the negative log probability is just 0.5 d log 2 pi plus 0.5 norm of z squared. So basically what this is telling us that if I want to compute the probability of any vector z as given by the standard Gaussian, this is to within an additive constant simply proportional to the squared norm of the vector itself, right? And so using that, if I want to minimize the error between x and x hat when I train my encoder, I also want to impose the constraint that z comes from a standard Gaussian. So I'm going to impose the additional constraint that the KL divergence between the distributions of Z that I see in the training data and the standard Gaussian is minimized. And minimizing the KL divergence is the same as minimizing the negative log likelihood of Z as computed using a standard Gaussian. So that becomes easy. We know that the negative log likelihood of Z, we just saw this, is going to be, there's an additive constant square root of 2 pi raised to d, but that doesn't really matter because that cannot be, that's a fixed term. So what we really want to do is minimize the squared norm of Z's. Because again, remember, going back to the standard Gaussian, the negative log probability of finding Z is simply this additive constant which doesn't depend on Z plus 0.5 times the squared norm of Z. So basically minimizing the negative log likelihood is the same as minimizing the squared norm of Z, which is the same as minimizing the output of the encoder in response to X. And so the overall training strategy for this autoencoder, where we impose this additional constraint that Z's must come from a standard Gaussian, is going to look like this. You want to find the encoder and decoder parameters theta and phi such that the squared norm of the error between the output of the decoder and the input to the encoder, x hat and x, is minimized, while simultaneously the squared norm of the output of the encoder, which is Z, is also minimized. Lambda is a weighting term which tells us how important it is to enforce the Gaussian distribution on Z, standard Gaussian distribution on Z. It's something that's a hyperparameter that can be set according to the results we get. So is this making sense so far? Fairly straightforward, right? Here's your second poll. And second, guys. Okay. Someone on Zoom, what's the answer to the first question? Zoom?
It's true.
And what about the second one?
It's false.
So a regular AE trained to also minimize the length of the hidden representation implicitly imposes an isotropic Gaussian distribution on Z. So this we've seen. That doesn't mean that the data can escape from the manifold. The decoder is still only able to generate data on the manifold. All we are doing is that we are training the model so that in addition to learning the manifold, it's somehow ensuring that the Z values themselves for the training data come from a standard Gaussian, which enables us to sample these Z's to generate new data, right? But then we're not done. This model does not capture the entire distribution. It doesn't capture all of the variation in the data. Why so? Here, the generative portion of the model is just the decoder. Once you train the model, you can throw away the encoder. Then you can just draw Z's from a standard Gaussian and feed it to the decoder, and you expect to see authentic samples come out of the decoder. But then the decoder has a constraint. It can only generate data on the low-dimensional manifold in the space. So here, for example, when I trained the decoder on the spiral, pretty much every single output that came out of the decoder lay on the spiral except in the regions where the Z was unknown. But it still just represented a one-dimensional curve in the two-dimensional space. And pretty much all data that the decoder could generate was only on this curve. Or if in higher dimensions, if my Z was a two-dimensional Gaussian, then all the Z represents a plane, a Gaussian distribution on a plane, the decoder is going to morph this plane into some kind of a curved two-dimensional surface in the higher dimensional space. And any sample that I feed to the decoder is only going to lie on this plane. It's not going to be able to escape off this plane. And the problem is that the actual dimensionality of the data cannot be known, right? What is the dimensionality of the manifold on which faces lie? We have no idea. So when we take a guess, we are probably going to get it wrong, which means that a manifold that we are forcing the data to lie on will not capture everything about faces to begin with, number one, right? And then number two, even if you manage to capture the dimensionality of this principal manifold perfectly, there is always going to be some variation of this manifold for the natural data. Real data don't lie exactly on this manifold. They're going to lie close to this manifold, which means that in both cases, even when we get the dimensionality of the manifold right, there is variation of the manifold which our model is unable to generate. When you get the dimensionality wrong, obviously there's going to be variation of the manifold, which your model does not capture. So how do we deal with this? To account for it, we have to extend our model. We're going to assume that the actual data that you observe is obtained by adding noise to the output of the decoder. And so the model now is updated to saying Z is generated. It's put through the decoder. It generates some X hat, but then you add some distribution, some noise, which is full dimensional, and allows the data to go off the manifold into the higher dimensional space. And so this is the entire model. And the noise now accounts for the variation of the manifold. But then, if you want the manifold to capture as much of the data structure as you can, then you want to train the model to minimize this error. If you allow this noise to be large, then whatever manifold you learn is going to be completely rubbish. So you want to train the manifold to make this error as small as possible. And this ensures that it has captured the principal manifold most effectively. And the typical assumption that we will make is that this noise is Gaussian. Once again, why have we got zero mean Gaussian? Why? If the noise had a mean that was not zero, then the decoder itself could just add this bias and reduce the error. Secondly, if the noise had any kind of structure, then you expect that the decoder would actually learn the structure if it's trained properly. So if everything is done right, the only portion that's left in the noise must be the most unpredictable portion of the data. And we know that the most unpredictable distribution is the Gaussian distribution. It has the highest entropy of all distributions for a given variance. And so the typical assumption is that the noise is uncorrelated Gaussian and it's independent of Z. Anything that varies from this assumption can actually, in principle, be captured by the model. But then this has a consequence. And the consequence is this, that the moment you say that I'm adding noise to the output of the decoder, that means there's no longer a one-to-one correspondence between what went into the decoder and what came out of the decoder, because for any input, depending on the noise that you add, the final output could be different. And so now here is the whole model. The decoder is now a generative model for the data. It has a generative story for how the data are produced. You have some k-dimensional vector drawn from a standard k-dimensional Gaussian that's passed through the decoder. This results in a data lying on some k-dimensional nonlinear surface in the data space. Then a full rank, low amplitude Gaussian noise is added to it to generate the final output. And the actual data distribution itself, according to this model, is a fuzzy region around the surface. And so this is the model that we have to learn, right? Now, how would we learn such a model? What would our training data be? The training data for our model, obviously, anytime you have an input-output relationship, then your training paradigm says, give me input-output pairs. Give me the z's and the x's. And if you give me a collection of z's and x's, I can train them train the parameters of my model. So if I had z's and x's, then I can learn the phi, just by minimizing the error between x and d of z, right? This is what we can do. But then, and again, this is what we want to do, because by assumption, the noise is the smallest possible correction that we would need to have, right? The problem is, when no one's giving you the z is a latent variable that you don't really observe, right? So if no one's giving you the z, where will this z come from? How would you do it if I had to give you this problem? Anybody? Anyone's on Zoom? How would you get a z in this case?
Use the encoder.
Here you can use the encoder, right? We want to estimate the z. And so the encoder estimates the z that permits us to use the phi. And so here is the model. But then we are still not done. Why? Because we are adding this noise E at the end of the decoding, right? Which means that you can't really be sure what the z is. There are many different z values, each of which would generate a different x hat, to each of which, by adding an appropriate noise, you can end up at x. So for any given x, because of the noise E, the z's that could have generated this x cannot be uniquely identified. In fact, the z's will have, there's an entire distribution of z's. Remember, the noise is Gaussian, and so the z that goes with the smallest amount of noise is going to be the most probable, and then as you increase the noise, those z's are going to be increasing, less and less probable, but then there's a distribution of z's that could all have generated this x with different probabilities. And so what we want our encoder to do is to actually learn the distribution of z's that could have generated this x rather than a unique z, because a unique z doesn't exist, right? And so this is what gives us the variational autoencoder, because this process of finding an encoder that characterizes the distribution of z such that z's drawn from this sample are most likely to end up being this training instance that you saw. That process utilizes the maximization of a variational lower bound on the likelihood of the data. We won't get into the details of it. The actual algorithm itself will be obvious from the lecture. And so here is the variational autoencoder. You have an encoder that for any given x computes the distribution P of z given x for that x. Then the decoder tries to convert the expected output of z's drawn from this distribution to the training instance. Now, we're learning the encoder is generating an entire distribution, right? And so all of these, every single point in the space, in the space of z's, could potentially be converted to x, but the kind of noise that you would require to add to it will have different probabilities. So there's an expected output where things that require a lot of noise will have much lower probability than things that require very little noise. And so you want the decoder to convert the expected output from z's drawn from this distribution to your x, right? But again, characterizing this expected distribution for this nonlinear complex function is hard. So more practically, what the decoder will try to do is to convert a typical sample z drawn from this posterior distribution P of z given x to x. Is this making sense to you guys? Right? Okay. And so, yeah.
Now that we have put it in this way, do we train the whole thing end to end?
Yes, we do. Right, and that's what we're going to do, right? So here is what we need to do. To train the encoder, we want to estimate the thetas in the encoder such that when you sample, such that the z's that are drawn from this distribution P of z given x produced by the encoder are highly likely to generate the data x, right? You at the back, hello? Do you mind leaving the classroom if you want to work on your assignment or whatever it is?
Following along the slides on my phone.
Okay.
It's easier to look at it.
All right, okay.
doing any other work, I promise.
Okay, sure. So we want to estimate the theta to make the z's that can be decoded into x hat values that are closer to x, more probable, right? That's what you want. The encoder must produce a distribution so that the most likely z's are most likely to be converted to x hats, which are really very close to x. And the decoder, you want to estimate the decoder parameters phi such that when I draw samples from this distribution of z's and try to convert them to x, the amount of noise that I add to it is minimized, right? Make it as small as possible. Again, this makes sense? The overall layout over here. Guys on Zoom, this makes sense? Is anybody paying attention? Is there any chat on Zoom? Okay. Just keep track. I don't think people are really paying attention. That's okay. That's their problem. So this is just speaking of converting the autoencoder itself. But then there's the final bit, right? We wanted to impose a statistical constraint on Z. And the statistical constraint on Z was that Z must be a standard Gaussian overall. But now, the conditional distribution of Z for any given X. What do I mean by the conditional distribution of Z for any given X? I have Z, and Z has a standard Gaussian distribution. If I pick any Z from this and I pass it through my decoder, it's going to generate faces and so on. But then if I consider any one face over here, this face could only have come from Z's in this region. Z's from other regions will generate other kinds of faces. So the conditional distribution of Z given the input is this guy, right? And so, again, the business of the encoder is to find this conditional distribution of Z. It specifies the region of Z from which the specific Z that produced that particular trading instance is most likely to have come. We know that the overall distribution of Z is a standard Gaussian, right? So how do these two combine? Here's what it means, right? What does it mean for the overall distribution of Z to be a standard Gaussian, but the conditional distribution of Z for any given X is some localized region? What this really means is that if I take every possible face, right? Every possible face, and look at the distribution of Z's that could have generated all of these faces. Each of these faces is going to come from a different region of the Z space. But over the entire set of faces, if you look at the overall distribution of Z, that's going to be a standard Gaussian. That's what this means, right? So this means that if I integrate P of Z given X over all possible values of X, then basically the expectation of P of Z given X over all X, that is going to be a standard Gaussian. That makes sense to you guys? Over here. And so we want to train our model such that the combined posterior over all possible X is a standard Gaussian.
I have a question, Prof. When you were explaining and then you were writing on the board, the audio was, when all the times you've been writing on the board, the audio has been, really, really bad. So I couldn't hear. So perhaps because where you're standing right now, I can hear you perfectly. Can you repeat what you were writing on the board? Because
So
I
what
didn't get anything. There's just a lot of, I can't get it.
So what we are saying is that the overall distribution of Z is a standard Gaussian. But if you take any specific face, that couldn't have come from all possible Z's. For any given specific X, the region of Z that could have generated that X is very localized, like one of these ellipses here, right? And so different X's could have come from different Z's. So each of the ellipses in the figure represents maybe the typical set of Z's for a specific X. And so when I say the overall distribution of Z is a standard Gaussian, what this means is that over all possible X's, if you look at the values of Z's, that distribution is standard Gaussian, which means that the union of all of those ellipses must be a standard Gaussian. And mathematically speaking, what that means is that the expected value of P of z given x is a standard Gaussian. That answer your question?
Yes, it does. Thank you.
And so here's the thing. We want P of z given x to be a standard Gaussian. The expected value of P of z given x to be a standard Gaussian, which means we must characterize P of z given x. But how do we characterize P of z given x? This becomes a problem too, right? The problem is the decoder is a very ugly, complicated function. So if I give you any given x, and I ask you to work your way back through the decoder and find the z's that could possibly have generated x, that's going to be very hard because D is ugly and transforms the data in a really ugly manner, right? So it's not possible. It's in general not possible for us to compose an encoder that gives us P of z given x exactly. Instead, what we will do is to try to approximate it. Our encoder is not going to give us P of z given x. It gives us some other distribution q. And the objective is that when you train the encoder, the q that it computes must be as close to the true posterior P of z given x as possible. That makes sense to everybody? The distinction between the q and the p. P is hard to characterize. We cannot really learn, in most cases, we can't really even know what it looks like. There's no formula for it. And so we're going to instead come up with an approximation q, which is as close to P of z given x as possible. And so,
Quick question.
yeah.
So I remember you said earlier that we use the encoder to generate some Z's that are used for training. So what you're talking about here, which I guess is learning the encoder,
Yeah.
like, do we also need to generate some sort of data? Like, is it generating its own training data? Or if you could clarify that, I think that'd be a little
Okay,
helpful
so
for me.
here's the entire process going back. What we are trying to do, so remember, this was the original model, right? From x's, we got the z's and tried to convert the z's back to x's. This was how the training was done. The encoder and decoder jointly trained. You get
Yeah.
that? Okay.
Yes.
Except that it's impossible for us to identify a specific z that the encoder must generate that gets converted to this x because there are many z's that could have generated x, right?
Yeah.
So which means that the encoder can no longer just generate a specific z. It must produce the distribution of z's which could all have been converted to this x. That answer your
Okay.
question? Yeah,
So
right?
is that what we're talking about, like, right now? Or I guess I'm just a bit unsure. Like, if the encoder starts out untrained, then how are we
Okay.
using it to generate the Z's?
So yes, so the whole thing must now be trained. So the encoder must be trained so that it generates, it identifies the distribution of z's for each x. And the decoder must be trained so that z's that are obtained from this distribution all have a very high probability of being converted to x. And this must all
Okay.
happen together. That answer your question?
So, so I guess one thing I'm just unclear about is like when we're training the encoder, what type of data are we using? Like, are we passing it through it or?
So here's the thing. We're using the same x. I give you images of faces,
Mm-hmm.
and you're going to train the encoder to generate a distribution z, and you're
Mm-hmm.
going to train a decoder that converts z's from this distribution to x. It's the same data. X is going in and x is coming out,
Ah, okay. Mm-hmm. Okay,
right?
I think I get it. Thank you.
So here's where we are, right? The encoder is computing an estimate of q of z given x, estimate q of z given x, which is supposed to be as close to as possible to p of z given x. And how do we make q and z as close as possible? We want to minimize the KL divergence between q and p. But then For this, I say I want to say that the expected KL divergence over all training instances must be minimized. But then to do this, I need P of z given x. And we started off saying P of z given x is not characterizable. If it were characterizable, why would I need an encoder to come up with an approximation? It would give me the actual P of z given x, right? And so we're going to have to manipulate things a little bit. And how so? I rewrite things. And so the KL divergence between Q and P is the expected value over Q, meaning over samples of Z drawn from Q, of log of Q over P, which I can write this as, log of Q over P is log of Q minus log of P. So it's the expected value over Z samples of Z drawn from Q of log of Q minus expected value of over Z drawn from Q of log of P of Z given X. Now P of Z given X using Bayes' rule can be written as P of Z times P of X given Z divided by P of X. So I can expand this right hand side out, and so the second term becomes this minus of the expected value of Z drawn over Z drawn from Q of log of P minus, so these two are minus because they are in the numerator, the expected value over Z drawn from Q of log of P of X given Z. Now this is not Z given X, it's X given Z, plus expected value of over Z drawn from Q of log of P of X. Now observe that log of P of X is not a function of either the encoder or the decoder. It's just the probability of the actual data. So this log last term doesn't really matter a whole lot. So, but these first two terms, expected value of over Z of log of Q minus expected value of Z of log of P of Z. Earlier we started off with P of Z given X, and this was the KL divergence between Q of Z given X and P of Z given X, right? So if I take these first two terms, that simply ends up being the KL divergence between Q of Z given X and P of Z, not P of Z given X, but P of Z, okay? And then the second term here is the expected value over Z of log of P of X given Z, and this third term is not really a function of the network parameters. So what is this first guy, right? This, when I minimize the scale divergence, I end up basically just having to minimize these first two terms, which is the KL divergence between Q of Z given X and P of Z minus the second term. And now the second term, P of X given Z, is the probability, negative log probability of the data X given Z. This is simply the negative log likelihood of the decoder. So minimizing the second term is the same as saying I'm giving you ZX pairs, train me the decoder. So the second portion just ends up being the portion of the loss that trains a portion of the loss that trains the decoder. And the first portion, what is this guy, this first term? This first term is the KL divergence between Q and P of Z, which we assumed was a standard Gaussian, right? And so we must minimize the expected divergence between the distribution Q out by the encoder and the standard normal with zero mean and unit variance. And if we do this, you'll get a pretty good approximation of P of Z given X, right? Remember, Q was supposed to approximate P, right? And so, again, this is the expected KL divergence between Q of Z given X and the standard Gaussian. But then you don't want to go through for that, and what is the expected KL divergence? The empirical version of it is the average KL divergence between Q of Z given X and the standard Gaussian computed over the entire training data. We still have to specify what is Q of Z given X. I've just written a random formula over there. What is it, right? So the encoder now must model this Q of Z given X. We know how neural networks can give you vectors. How does it give you a distribution? It doesn't give you a distribution. It's going to give you something, parameters of the distribution, right? Yeah.
Is this assuming our training data is normally distributed?
You're making no assumptions about the training data. The normal distribution is only on Z.
And that's what the encoder is doing.
Yeah, the encoder, that's the latent variable. We're assuming that the latent variable is normal, that's it,
Okay.
right? And so again, Remember that Q must approximate Z as closely as possible, the distribution of Z that could generate any X. And the decoder converts Z to X hat, such that, and the decoder is highly nonlinear, right? So how do we represent Q? What is Q? We'll get back to that. But then we want Q to have a form that is as similar as possible to the probability distribution of P. Q of Z given X is approximating P of Z given X, right? What does P of Z given X look like? Let's take a look. Now, if I take any X, there's an entire region of the input space, of the latent variable space, Z, that could have been mapped onto X because I'm adding noise at the end, right? But because this function, the decoder D, sort of warps the space, warps the Z space, and converts it to a very nonlinear manifold on the output side, if I give you any X, it's impossible for me to go back and identify the region of Z on the space that could have generated X. So we go back and, the math is ugly. Anytime we get ugly math, our solution is to simplify. And here's how we will do it, right? Here's what we see. We know that the distribution of X given X hat is Gaussian. Why? X hat is the output of the decoder. And all you're doing is adding a Gaussian noise E to it to get X. So P of X given X hat is Gaussian, right? It's just that going back here and characterizing P of Z given X is not possible. But then let's go and look at a standard Gaussian. We know that the overall distribution of P of Z is a standard Gaussian. That's what we assumed. And this means that if I slice this distribution at along any plane, on that plane, so if I've got two variables, Z1 and Z2, then the joint distribution of Z1 and Z2 is a standard Gaussian. If I give you Z2 and say, what is the distribution of Z1 at this Z2? It's like slicing the distribution at Z2. And when you slice it, that distribution is still going to look like a standard Gaussian. So for any Z2, P of Z1 given Z2 is going to be a standard Gaussian, because in a standard Gaussian, all of the variables are independent of one another, right? So the interesting thing is it doesn't matter which angle I slice this isotropic Gaussian at. If I slice it along any plane, the distribution on that plane is still going to be a standard Gaussian. That's the property of an isotropic Gaussian. And so, and a plane, of course, is, any plane given by AZ equals B. That's the equation of a plane, right? If I slice it, it's going to be, on that plane, the distribution is going to be standard Gaussian. More generally, instead of slicing it at a plane, if I slice it along a very gentle curved sheet, right? Curved manifold, the distribution is still going to be, meaning for any nearly linear functions, the conditional distribution on that curve is still going to be more or less Gaussian. It can be well approximated by a Gaussian. So if I say, instead of saying P of Z given AZ equals B is a standard Gaussian, if I get P of Z given F of Z equals C, where F of Z is kind of a nonlinear function, so long as F of Z is not wickedly curved, it's perfectly reasonable to approximate that, to say that the distribution of Z on this curved surface is also more or less Gaussian. And what do I mean by saying nearly linear? It means that the variation between a plane and this curve and this curved surface should be small in high probability regions of Z. That's about it. And so once we realize that, I can actually say that the probability distribution of Z on any curve is also approximately Gaussian. The one distinction between having a perfect line, plane, and finding the distribution on a curve is that it's kind of depending on the nature of the curve, the mean and variance of this Gaussian are going to be slightly different. And so earlier, when you were just slicing it along the plane, it didn't matter which plane you took, the variance was 1, right? Here, because it's curved, the mean and variance are going to depend on the function f. This makes sense to everybody so far? It's an approximation. And it's an approximation because of the properties that is mostly valid because of the properties of the standard Gaussian. So that gives us an expo. Okay, 15 seconds, guys. Okay, what's the answer to the first question? True. And what about the second? True. Right? If Z is a random vector with an isotropic Gaussian distribution, the conditional distribution of the projection of Z on any affine plane is also isotropic. And on any curved surface, it's approximately Gaussian for surfaces of low curvature. Right? If it's an affine plane, it's isotropic. It's unit variance. If it's curved, we don't know exactly what the variance is. You'd have to estimate it, but it's approximately Gaussian, which means that I can assume that the Q of Z given X is kind of Gaussian, right? And so here is the overall training process. The encoder computes the distribution Q of Z given X for any X, which is an approximation to P of Z given X. The decoder tries to convert samples from this Q of Z given X to the X for each, back to the X for each training instance X. And when you train the encoder, we want to estimate the theta such that the Z's drawn from this Q, when converted by the decoder, are as close to X as possible. And when you train the decoder, again, same thing. You want the Z's to be converted to X hats that are as close to X as possible. Both the encoder and the decoder now have the same objective. The output of the decoder must resemble the original training instance as closely as possible. We have the additional constraint that the average Q of Z given X over all training instances is as close to the standard Gaussian as possible. And what is Q of Z given X? Going by the principle that we just saw, we're going to assume that it's a Gaussian. Once I decide that Q of Z given X is a Gaussian, now it has a functional form. It has two parameters, a mean and a variance. And all I need to do is to estimate the mean and the variance of the Gaussian, and I'm done. So the encoder now is computing two terms, the mu and the variance sigma, and Q of Z given X is basically a standard Gaussian with this mean and this variance. So this is how we compute Q. And we want to compute mu and sigma such that the average KL divergence between this Gaussian and the standard Gaussian over all training instances is as close to zeros, as small as possible, right? And additionally, for a Gaussian, the covariance matrix can be a full matrix, but for convenience, we're going to assume that it's diagonal, just for mathematical tractability. And so we want to estimate the theta, which is the specific encoder parameters that make Z's sampled from X as close to the training data as possible, right? How do you do it? So again, how do you do that? First, even to see how the decoder is trained, encoder is trained, we have to look at the decoder, because the objective is to make the output of the decoder X hat as close to the training instance X as possible. And the input to the decoder consists of samples drawn from Q, right? And so let's look at what is the probability distribution of X, the training instances, given Z. Once I give you Z, because the decoder is deterministic, giving you Z is the same as giving you X hat, because I can just pass the Z through the decoder and I get X hat. So what is the residue left? The residue is the noise that we're adding. And the noise we are adding is, we assumed, is a Gaussian, right? It's with some variance C. It's the noise has mean 0 and variance C. So P of X given z is the same as p of x given x hat, which is a mean, a standard Gaussian with mean x hat, which is d of z, and variance c. Is this making sense to you guys? This one here? Right, straightforward, right? Furthermore, I'm going to assume that the covariance of the noise is diagonal and isotropic. Why can I do that? It's a perfectly valid assumption because anytime you have a full covariance, there's some structure to the noise, right? And that can be captured by tilting the plane that the decoder is learning. So it makes sense for us to assume that the covariance of the noise is diagonal and it's isotropic, right? With some variance sigma squared. It makes it it's perfectly reasonable to even assume that the variance is just high. Okay. So when I do this, the log probability of x given z is simply the log of this Gaussian computed at x, which is going to be minus d over 2 log sigma squared. There's an additional 2 pi term that I'm ignoring, minus 1 over sigma squared x minus d of z whole square. This is just the log of this Gaussian with the 2 pi term, with the irrelevant terms removed, right? And I want to estimate the decoder that maximizes the log probability of my data. Basically, I want to estimate the decoder such that when samples are drawn from Q and pass through the decoder, I want to estimate the encoder such that when samples are drawn from Q and pass through the decoder, the training instances that I do have are highly, highly probable. And so this is the log probability of the training instances for any given z. And so this guy is what I want to maximize, right? And the encoder must be trained to maximize this guy. But then this term doesn't have a theta in it, does it? Do you see any encoder parameters over here? The encoder has a theta in it. Do you see them here? Where do you, so what do you think the encoder is influencing here? How does the encoder figure here? Anyone?
The value of z.
Because the encoder, so we want to learn the parameters through using back propagation, which either maximizes the log likelihood of the training data or minimizes the negative log likelihood over all training instances. But what you really want to do is to minimize this over the minimize the expectation of this over z for each training instance, which is complex. Anyway, the point is, this is implicitly also a function of the encoder parameters, and we want to minimize this loss with respect to the encoder parameters, and the encoder parameters themselves compute, right? And where does z come in? For each training input x, we again, keep in mind, what we really want to minimize is this term on top for all z's that could have been generated from Q. But you don't want to be computing this over all z's. So typically what we will do is just sample one z from Q. So for each training instance, we're going to compute a ZQ, and ideally you minimize the loss over the entire distribution Q. Instead, we're going to sample a single z from it, and you're going to minimize the loss over that z. And so the z is obtained as a sample from the standard Gaussian with the mean mu of x and variance sigma of x, which are both functions of encoder parameters theta. And now, sampling is not a differentiable process. But then there's a standard reparameterization trick. How do we generate data from a Gaussian with some arbitrary mean and arbitrary variance? So I'm going to try to point this at me. Hopefully you can hear me. So if I have a standard Gaussian, then pretty much any coding language in the world is going to give you this times n. If you run it, it's going to give you a sample from a standard Gaussian, right? But if I want to sample from a Gaussian that is mean mu and variance I, how would you do this? What would you do?
Add a mean.
I can just add a mean, right? This is easy. If I want to sample from a Gaussian, which is mean mu and variance sigma squared, then what do I do?
Fine.
I would have to scale it up first by sigma, and then add a mean. Right? And that's going to give me my Gaussian from this distribution. So here, if I want to estimate, draw a sample from a Gaussian with mean mu and variance sigma, I'm going to draw a sample epsilon from a standard Gaussian, multiply it by the square root of the variance, which is the standard deviation, and then add the mean, right? And once you look at this, epsilon is a random sample, but now it has parameters. It has parameters mu and sigma, which are functions of theta. And so z can now be differentiated with respect to theta because the derivative of mu with respect to theta plus the diagonal of epsilon times the derivative of the square root of sigma with respect to theta. Right? And this is a nice closed form, which you can get using back propagation. This makes sense? Right. And so here's what we have. I have in this loss function z is mu plus square root of sigma times epsilon, where epsilon has been drawn from a standard Gaussian. And now using that, I can compute the derivative of the loss with respect to theta, because the derivative of the loss with respect to theta is the derivative of the loss with respect to z, which is easily derived from the loss formula up there, times the derivative of z with respect to theta, which we can get from here, because z is a function of mu and sigma, which are functions of theta. Just using the chain rule repeatedly. This makes sense to everybody? All of you guys? Nothing complicated. We're doing this, it's all very simple, okay? And so we know how to estimate. So we've figured this out, how to compute derivatives with respect to theta. The next term left is to estimate the phi. That was about the encoder. The next term are the decoder parameters phi, which make the samples, make the x hat derived from samples drawn from Q more probable. Basically, we want to estimate the decoder parameter phi to minimize the error between x hat and x, same as before, right? And so this, once again, if I look at the loss function, the negative log likelihood was just this guy, right? The d times the log of sigma squared, which is the variance from the noise, plus the second term, which is just the error between x and d of z. And this is a nice quadratic. This can be easily differentiated with respect to phi. And you can get derivatives. And so the derivative of the loss with respect to phi and sigma squared are also both trivially computed. Does that make sense so far? Nothing complex, right? And the last one is the constraint on z. We want the average u of z given x to be as close to a standard Gaussian as possible. What does that mean? The KL between q of z given x, which is q of z given x we said was a Gaussian with mean mu and variance sigma, right? The Kullback-Leibler divergence between that and a standard Gaussian has a nice closed form formula also, which is given by, on the slide, it's the trace of the variance, which is basically the sum of all the diagonal elements of the variance, plus the the squared norm of the mean, minus the log of the determinant of the variance. So you have the determinant of the log determinant of the variance, which is a function of theta, the squared norm of the mean, which is a function of theta, and the trace of sigma, which is a function of theta. If this term is minimized, then you're minimizing the KL divergence between Q and the standard Gaussian. Now this guy has to be averaged over all training instances. So that's what we do. So now the overall loss simply becomes this. This first term is the KL divergence between the average KL divergence between Q and the standard Gaussian. The second term is the actual error between the output of the decoder and the actual training instance for a random Z sample from the Q for each training instance. And so now I have an overall loss function, and this loss function can be differentiated with respect to both theta and phi. And so I can train the model, right? This loss must be minimized to train the VAE. And the derivatives for all terms are trivially computed. Any questions? Yeah.
How do you get the derivative of the determinant?
So the derivative of the determinant over here, in this case it's easy, because if I assume that sigma is a diagonal matrix, it's a sum of diagonal terms, right? We have closed form formulae, but here it's particularly easy, right? And so here is the overall process for training the variational autoencoder. I'm going to initialize the decoder and encoder parameters. Then for each x, I'm going to pass x through the decoder, which simply computes the mean and the variance and gives me a standard Gaussian. I'm going to sample a z from it. I pass the c through the, for each x, I pass the x through the encoder, which gives me the mean and the variance. And so it gives me a standard Gaussian. I'm going to sample a z from this Gaussian, and I'm going to pass it through the decoder. That gives me an x hat. And now I have a loss function, which is this first term is the average of this term, trace plus the inner product of the square norm of the mean minus log of the determinant of the variance. So this I would this term plus the second term, which is the error between the output of the decoder and the actual training data. So if this is summed over your entire mini batch, that's your loss function, and that's what you're going to be minimizing, right? Now, where's the neural network? The decoder is a neural network. It can be anything. And the encoder, the only thing about the decoder is that it's going to be computing a mean and a variance for Q. The encoder D, so the decoder is a neural network, can be anything. Encoder over here, that's also a neural network. It's going to be computing mean and variance for each training instance. But otherwise, this is straightforward, right? Now observe over here that although I'm writing two different summations, in the process of training, corresponding to each x, there's going to be only one z, because you're sampling a z from the Q. So the overall summation is going to have the exact same number of terms for both components of the loss. And so once you've trained the network using back propagation, then the encoder, which computes Q, can be thrown away. The decoder is the actual generative portion of the model, and this is the generative model for X. And so once you've trained it, say if I've trained this on collections of faces, if I want to generate a new sample of a face, all I need to do is to sample a Z from a standard Gaussian and pass it through the decoder, and to within the fuzzy noise which moves data off the manifold, you're going to get an image which looks more or less like a face. Okay? So this is the variational autoencoder. Again, the variational autoencoder is an autoencoder with statistical constraints on the hidden representation. The encoder is a statistical model that computes the parameters of a Gaussian. This is the encoder. The decoder converts samples from the Gaussian back to the input. And the decoder here is a generative model that, when excited by standard Gaussian inputs, generates samples similar to the training data. Okay? Any questions? Yeah.
Explain again, why do we have like the noise instead of to try and remove the data from manifolds?
So noise, because if you don't have the noise, then it's an approximation, right? So the noise explicitly accounts for the statistical variations of the data of the manifold. That's it. And we know the noise is unpredictable, which means that accounting for this explicitly gives us benefit. If you didn't, then the entire model actually ends up becoming much simpler. But again, you have the constraints you impose on Z will be less satisfied. Now, the decoder again is the actual generative model, and you're never going to actually consider the noise when you're generating, right? The encoder is primarily needed for training. It can also be used to generate the approximate distribution of the latent space variable Z for any given input, right? Much like an autoencoder. Z is the latent space representation. And what is the value of Z for any given training data instance or any instance X? Once it's trained, I can pass any X through the encoder. And what the encoder will give you is the mean and the variance of all possible Z's that could have generated the X. But if I had to pick a specific Z, I'd probably pick the mean because the mean is the most likely one, right? Okay, 10 seconds. Okay, anybody on Zoom want to answer the first question? Zoom?
It's true.
Okay, on the second question, is the first statement true or false? First, true or false, guys? True. Okay, what about the second one?
True.
True. And the third?
True.
What do you guys think? Can somebody say true or false loud?
True.
Everything is true, right? So the variational autoencoder is a generative extension of autoencoders that models probability distributions. The standard variational autoencoder assumes that the latent representation of Z is an isotropic Gaussian. It requires addition of Gaussian noise to the output of the regular AE to permit the output to fill the space. Otherwise, you're going to be forcing it to lie on the manifold, right? And yeah.
When we actually use the model, we don't add the noise.
No, the noise is just
For training.
Yeah, you don't really need to, right? You could. Go ahead.
So you use that noise to basically get closer to the higher dimensional.
To get the right manifold and get the right distribution on the manifold.
Okay.
Right? Otherwise, it provides us greater control. Right? Now, the VAE model requires addition of Gaussian noise to the output of the regularized AE to permit the output to fill space beyond the lower dimensional manifold. And this becomes particularly important if you get the wrong dimensionality of the manifold. Right? And so, and the decoder can be used to generate samples from the distribution of the data it's trained on if the input to it is drawn from a standard Gaussian. So here are some examples from the original VAE paper. The top one, this was a VAE trained on the MNIST data, and they used it to generate new data, and you can see that it actually generates perfectly good digits. And the second one was a VAE trained on faces, and you can see that it generates fairly good faces. Now, what is the one characteristic that you see about these things? Are these detailed, or are they blurry?
Blurry. On the edges, they're blurry.
Mm-hmm. They're blurry, right? So I'll get back to that. Now, the latent space captures the underlying structure of the data. Basically, you're saying the data lies on some manifold, and the latent space is basically capturing the manifold. which means that if you travel along this manifold, you're probably traveling along the space of faces. And so people use this for manipulation. You can use it for manipulation. Here's an example where you have, you take two faces, you get the z, the mean z for this face and the mean z for this face. Take a z exactly between the two and put that z through the decoder, and you get a half smiling face, right? Here's one where again there's the same face, and then this is the other end. You take the mean z for both these faces, which are real, pass it through the decoder, and you get something which is partially frowning. It does a very good job of actually capturing the latent structure. But, so, to conclude, the VAE is a simple statistical extension of the encoder. It's an excellent generative model for the distribution of P of X. And you have various extensions like conditional VAEs, which impose conditions like class, generate a male face, right? Where you have a conditional variable in addition to, as an additional input to both the encoder and decoder. There's a lot of literature on it. But then, this model has two key limitations. First, why did we need an estimate, an approximation to the, an approximation Q? Why was the decoder not actually computing P of z given X? Why did we say we wanted a Q and rather than the P?
Because it's difficult to calculate.
The decoder is very complicated. It's hard for us to go back and find out because of the ugly manner in which the decoder manipulates the space. It's hard for us to go back through the decoder and find the specific region of the latent space that could have generated that data. And there's a solution to this. We can try to make the decoder invertible. And that gives us a class of models called normalizing flows. Hopefully we'll cover that in the next class. The other thing is the fact that if you look at this guy, these spaces are blurry. Why is it blurry? So here, the assumption, if I have a clean face and I have a blurry face, what will the difference between the two look like? Will it still have features of faces? It must, right? Because the blurry image is not a real face and the difference is a face. Whereas our assumption was that when you passed Z through the decoder, this noise was uncorrelated to the actual data. If the decoder is producing blurry faces, is the error actually uncorrelated? No, because the error actually looks like a face, right? So what does this mean? It means that our model is not doing a perfect job of completely decorrelating the noise. Why is that? Why that is that when you start from a standard Gaussian and try to go to a rather complicated distribution, the distance you must traverse is large. It's very huge. What would be better if your initial distribution itself was somewhat closer to the final distribution you wanted to begin with? Remember, we just chose P of z to be a standard Gaussian. There was no need for us to choose P of z to be a standard Gaussian, right? If P of z were closer to the target distribution, the decoder would have to work less hard, right? And in that case, you'd expect to do a better job of modeling the distribution. But then where would you get this guy from? Where could you get that guy from? Anyone?
Encoder.
Mm-hmm.
The encoder.
But the encoder is giving us a standard Gaussian, right? So here's the thing. We think the decoder one went from standard Gaussian to here in our first place. That was a decoder of an autoencoder. But in attempting to give you this, it actually gave you this. Right? That gave you the blurry faces. So why don't I use that itself as a seed for my autoencoder? So which means that I can make my P of z itself be the output of something. Right. But then I can sort of nest it. I can have an autoencoder, seed an autoencoder, seed an autoencoder, seed an autoencoder, seed an autoencoder. That gives us this one particular version of this gives us this famous class of models called diffusion models. And so we will cover that also in the next class. Okay? Thank you. Any questions? Thank you very much, guys.